9, OS support. We have 5 talks this morning. I ask you to ask many questions, just out of self-interest, so I don't have to ask questions. So please, everybody pay attention to the talks. We have fantastic talks. Ask questions afterwards. Give the speakers a hard time about their good papers. And so the first presentation this morning is Sandia. I hope I pronounced that somewhat correctly. It's a collaboration between Georgia Tech, Virginia Tech, and University of Toronto. You're a PhD student, and the floor is yours.
Thank you for the introduction. Hello everyone. Today I'm going to talk about how to use hardware timestamping to design scalable ordering primitive. I'm Sanidhya, and this is a joint work with Georgia Tech, Virginia Tech, and University of Toronto. So let's get started. As we know that there are a lot of machines coming up with large multi-core machines, for example, Supermicro or other kind of Intel machines already provide 4-socket to 8-socket x86 or Intel Xeon processors. Well, this trend is also true with other kind of architectures such as ARM. For example, KVM already provides 2-socket for 96-core machines. Well, this leads to huge hardware thread parallelism. But the question becomes is who are going to use it? Well, we have like databases, file system, operating systems, even like software transaction memory kind of approaches that try to exploit this parallelism. But the important question is, how are we going to execute the operations correctly? And the answer lies in the ordering. But the moment we start using a lot of cores, we start to face the problem of scalability bottleneck. Let me give you an example from the perspective of a sort of a transaction memory kind of a example. Here we have a read log update. Read log update is an extension of RCU, which was presented in SOSP 2015. It's an interesting work because it actually is an extension and it tries to modify the objects. It tries to modify the object in its own local log and maintains the linearizability or the correctness of the algorithms by using the clock, and tries to freeze the object by using epoch-based reclamation. Let's get into more details. Suppose we have these 5 elements in a linked list. So the way RLU works is like it will have a RLU header at the beginning of each element. And then suppose a P thread comes and wants to delete B and D. Or even tries to modify it. So what will happen is it will actually do this operation in its own log. At that time, the global clock, there is a notion which is being maintained for the snapshot, for maintaining the snapshot. What happens is, suppose we have another thread Q is coming up, which wants to read the whole list. In this case, what happens is like at the starting of the list, it will read the global clock value and write it to its own local clock, which is 22, and will start reading. Now P is about to commit the operation. At the time of commit, what happens is it just updates its clock because it has already done all the operations, and then changes its write clock value to 23 atomically, and then again updates the global clock value to 23. Since Q is on D list, D element, it actually is still behind the actual value. So it is on the older snapshot. So the Q will keep on reading the old snapshot, while P will wait until and unless the Q is able to finish until Q finishes the whole part. So what we can observe here is that the logical clock is actually maintaining the correctness, or we can say the ordering. And it is being maintained via atomic instructions such as fetch and add or compare and swap. Well, if we start looking at the inherent problem, let me give you a very simple chart or a graph from by taking 2 machines. We have like a Xeon Phi machine and a ARM machine, and the x-axis represents the number of cores and the y-axis represents the number of operations per microsecond for a RLU hash list benchmark with 2% writes. What happens in this case, like the atomic represents the actual RLU benchmark that we are running. What happens is like the maximum performance that we see is around 60 to 80 microsecond. On the Phi machine, denoted as Phi. Whereas on the ARM, after 48 cores, we don't see the scalability. There is a degradation. What if we could remove that part? Like what if we could remove it and replace it with something else, which we call here ordo? We can see that we can actually remove some of the scalability part. Now the question becomes is, how are we going to achieve the ordering with minimal timestamping overhead? Thus, we propose ordo, a simple monotonically increasing, so a simple primitive that provides the notion of a monotonically increasing clock, which relies on the current, instructions such as RDT-SCP, CNT-VCT in ARM, or like STIC instructions in the Spark side. And it has the kind of the clocks that it uses is like invariant in nature. What I mean by invariant is that the clocks are always monotonically increasing with constant skew, regardless of the dynamic frequency and voltage scaling, which is being guaranteed by the hardware. And Intel and AMD already confirms it. So if we want to use this, there are still two challenges. The first one is we cannot actually compare the two clocks. They are still not synchronized. So when I say synchronized, it means like they still have a constant skew between them or among themselves. The reason for this is that the cores actually receive, or whenever we reboot the machine, we actually receive the reset signal at varying times, depending on the socket. Since we have unsynchronized clocks, the question becomes, how are you going to apply it? How are the concurrent algorithms going to handle this? The way we try to use is like we come up with a very simple approach of like how can we actually embrace this invariant nature, the constant skew factor. What we try to come up with the approach is like how can we have a global uncertainty window which can say that once we have crossed this point, we are destined to have a new timestamp. This in a way will actually provide a notion of a globally synchronized clock. But the question becomes is like how are you going to measure that offset or like that global offset window? So even if we talk from two clocks perspective, so two cores perspective, how are you going to say that the measured offset is going to be greater? Here we have an invariant which we call as which should have the invariant as the following, that the measured offset should be always greater than the physical offset. So the physical offset is already coming up because of the reset signal, and the measured offset is the physical offset plus some delay that we introduce. So let me give you a very simple example of what we mean by that. By the way, we call this uncertainty window as the ordo boundary, after which we can actually easily compare the clock or can say that the new timestamp is there. Suppose we have here two cores, C1 and C2, and this is the timeline, like the cores have the time going on. At T1, we actually just do a simple timestamp instruction and obtain 0 here. Then we do a simple write operation to the other core notified by memory, and then again calculate. Thus, going from C1 to C2 is actually 20 cycles. So this is our measured offset. But we keep on repeating this step again and again in order to reduce the overhead, because we may introduce some sort of software jitter, or like network overhead can come into the picture because or even an interrupt can come and can have a large value. We perform the similar step in the opposite direction as well, because we don't know which of the clocks are ahead. So in this case, we again perform the same operation from C2 to C1. For example, we again calculate a timestamp on C2, which is right now 50. We again do a write operation on C1 and then get T of C1 as 80. So here we get the time, going from C2 to C1 is actually 30 cycles. What we observe is that in both directions, we are seeing 20 and 30 cycles. In order to be conservative, in order to be able to use it for all the cores, across all the cores, or have a notion of a global synchronized window, we take a very conservative approach of taking 30 cycles. And we do this in a pairwise fashion for all the combinations of core. This we call as the order boundary, which actually provides the notion of once we pass that window, we know that we are ahead in the timestamp. In terms of application, it is actually, order can be applied to any timestamp based algorithm. In order to do that, we actually expose a very simple true time kind of API to the algorithm, such as like get time, which actually provides you the hardware timestamp without memory reordering. The other one is the compare time, like whether you can compare two timestamps or not. Here the catch is that we may have a sort of an uncertainty, whether the T1 is actually greater than T2 or T2 is actually greater than T1. In this case, we just return 0, or like, okay, we don't know. And the new time is, okay, it is guaranteed to obtain a new time once the order boundary has passed. The catch lies for the applications is how are they going to handle this uncertainty? So if we look at a very high level, it will be like, so if you want to convert any of the logical timestamping based algorithms, they have to rely on the physical clock. In this case, what we do is like we just directly use the compare time, and in most cases, we conservatively defer or revert the operation if we are uncertain. It is almost similar to having like a lesser timestamp. The other one is like we have to use new time if we want to guarantee a new timestamp value. in the case of physical timestamping, depending on the kind of algorithm we are designing, we may rely on all three of them. In terms of example, we actually already discussed about the core C1 and C2. Suppose we have a global offset of 30 cycles. And here we have again the same example of the list coming up from the RLU. What happens is P again maintains the, P again modifies B and D, and its own local clock is 22 when it started the operation. Now Q comes, and Q's core is actually is at 50. And what happens at this time is it will read its own clock, which will come out to be 50, and then it will start reading the clock, the whole list. At time of commit operation, since P has been doing something, its value comes out to be 150. Well, 150 is, according to the offset compare time value, it is still very large because the Q's local clock plus the global offset is still smaller. In this case, Q will keep on reading the old value, old objects, and P will keep on waiting using the RC-based epoch reclamation. This, in terms, provides almost the same kind of guarantee that we were having with the atomic clocks. We have actually modified, in our paper, 5 different algorithms. The first one was the RLU. The other one is the TL2 algorithm in the STM, and 2 database concurrency control algorithms, OCC and MVCC. We have also applied oplog to the Linux for the RMAP data structure in order to scale the Linux forking functionality. Please refer our paper for more details. In terms of evaluation, we first want to show what is a measured global offset that we can see, and how extreme is the scalability if we are just doing a single operation of fetch and add, and what is the order's impact on the algorithms. In terms of evaluation, we have considered 4 machines. One is an 8-socket machine of Xeon 8-socket machine, single 256 core Intel Xeon Phi, a 2-socket ARM machine, and an 8-socket AMD machine. We empirically measured this offset, and what we can see here is that the minimum offset between any 2 cores comes out to be around 70 nanoseconds to 100 nanoseconds. Whereas the maximum offset, which is the ordo boundary, is in the range for x86 machine is around 270 nanoseconds, but for ARM machine we observe it's for 1.1 microseconds. The reason is that the ARM has a different clock which moves at a very lower frequency compared with all these machines, all the x86 machines have. Now let's look at a very simple micro benchmark example, when we are doing just fetch and add. Here, the x-axis represents the number of cores, and the y-axis represents the number of operations performed per microsecond per core. So all these are the representation of a machine, and what happens is the moment we cross 8 cores, we don't see the throughput decreases drastically. It actually, it takes around from 32 cycles to almost 200,000 cycles if we are using a Xeon Phi. But if we just rely on the hardware timestamp, including the ordo boundary, we are still almost stable because we are not putting any stress on the cache lines or on the contention, on the memory part, which is almost 17.4 to 285x faster than the atomic increments. Now I'll give a simple example for the RLU. Here we have a hash list benchmark and we are doing 2% writes. And we are evaluating the same as before for all 3 machines, for all 4 machines. So what happens is we can still see that at high core count, all these the algorithm is still suffering from the cache line condition just because of the memory, just because of the global clock. But RLU again has its own inherent limitation in terms of object copying and its locking, which are part of its limitations, which we cannot solve in this case. In terms of designing an algorithm, Ordo can actually simplify their design as well as understanding of those algorithms. Because now the software doesn't have to maintain the clock by itself. It is being maintained already. Well, this is not always applicable because if we are not suffering from cache line condition, which we observed for one socket in the case of Xeon machine, is that the performance is better. But the moment we start having cache line contentions or because we are relying on global clock, we can't do that. We didn't consider any skew, but the thing is dynamic skew, but the point is that we have never observed it during our experiments. The other point could have been like, why didn't we do the thread ID based comparison? Because we already have a table. But the point is like, the moment we have large number of cores, it becomes difficult to maintain that table, and there is a possibility of thread migration. In summary, we present Ordo, a simple scalable timestamping primitive that actually relies on invariant hardware clocks, and it exposes a true time-based API to the user. We have applied Ordo to five concurrent algorithms, and thereby we have improved some of the scalability for some of the algorithms by 39.7x across the architectures. Thank you for listening to me, and with that I'll be happy to take questions.
So is the original global clock still based on the hardware clock or not? For the original RLU?
It uses atomic instructions. So like it maintains so it has a global clock variable, and will keep on updating so that's the notion of a logical clock. So logical clock is always maintained by the software. So I'm going to increment myself because I know, okay, I have done an operation, now I should increment it.
Okay, so your approach is based on the hardware clock?
Yes, so we try to use the hardware clock and then see what is going to happen.
So if in a multi-tenant system that you have multiple RLU locks competing with each other, so actually according to one of the talks yesterday, there could be time discontinuity for a particular program. So actually the time measurement of a particular program could be detonated based on the hardware clock. So how would you address this issue with your hardware clock? Because if the original clock is a logical clock, then that should be fine because that was the virtual time of the original data structure. But if this is a hardware clock, then there could be problems.
So are you talking from the virtual machine perspective or normal perspective?
Just the general multi-programming environment. So if you have a multi-program timeshare the same clock,
yes,
then your design may have a vulnerability to of correctness, I think.
I don't think so. Because the thing is like, you're still going to, so whoever is going to use a clock, so they will say the same value all the time, right? I don't see the problem with if you're even using the hardware timestamp based clock. Even if you have two applications are running, it doesn't matter because they will be, whenever this guy comes and then it has to see the time, yeah, it will see a later time, it can be deferred to a certain extent. But we didn't evaluate it for 2 or 3 benchmarks on that basis.
Okay, talk about that offline.
More questions? Oh, yes.
Hi. So what happens if the comparison is uncertain?
So if the comparison is uncertain, so we say like we have a very conservative approach. So for example, in the case of transaction-based, like for example, if you're doing RLU or taking any of these, we just defer or revert the operation, depending on what could have happened. So if you're committing and if you know like, okay, cannot compare, if I have a lower value, I'll just not proceed forward. So which is applicable for these kind of algorithms to a certain extent.
So in the RLU example, if the order boundary is like 50 and then the different timestamp difference is like 10,
yeah.
What would the reader do? Would it just drop it, or would it use a new version?
So if you take the example from so if the difference is only 10 and you're already if you're already at 50, it means like it's not the order boundary actually. It's like we have already crossed that. So we are having a new snapshot. So it doesn't matter.
Okay. Thank you.
Okay. Can I?
How do you deal with the case when the hardware clock wraps around?
Yeah, we haven't dealt with that, but like if you see the other works that actually talk about this, they actually say that it's fine because you're wrapping around, you can actually come back and do the same operations again. I mean, it doesn't affect much. Because all the clock will actually wrap around at that time. So there will be failure for some cases, but then you can start again from 0. So it will not affect much.
But it sounds like you might have some spurious ports or something.
Yeah, possible.
Right, when you go across it.
Correct. But still the thing is like the time is pretty big because we're talking about 64-bit clock, 64-bit values. So having that spurious aborts is going to take some time in terms of years. So I don't think it's going to be an issue.
Okay. We still have time for 1 or 2 more questions. I guess I have to ask some question. You are not ready to go. What about the skew? You said you didn't observe any skew. Is that hardware related because all the clocks are synchronized by hardware or derived from the same clock?
Yes. The thing is, like the platform hardware or the motherboard clock is actually driving the whole. It's actually synchronizing the clocks. So the thing is, like they maintain an on-core and off-core counter for each core, and the off-core value is being synchronized by the. So if you read so Intel has already a patent on this. Okay. So they actually talk about like how are they actually synchronizing this. So they are using the platform controller to synchronize, and then they are actually updating the value.
Okay. Yeah. Do you have any problems in virtualized environments?
We haven't tried there.
Because the counters are virtualized?
I don't think so. I mean...
the hardware clocks?
So I think the RDDSC is directly exposed. As we have done some experiments, we didn't see like they are being synchronized. They're virtualized.
So at least in SGX, you can have an exit on hardware clocks into the VM. Yeah.
So we haven't looked from that perspective, actually.
Okay. Then we should take that offline, talk a little more. Any more questions? Then thank you very much.
Thank you.
Okay, the next talk is given by Ria Rao. Hopefully I got that right. It's a collaboration between University of Texas at Arlington and University of Nebraska at Lincoln. And it's about garbage collection on multi-core systems. And hopefully we get the technical problems resolved.
Partially solved. Then we need to solve this problem first.
Yes. Oh, there.
Okay,
there we go.
I think we are good.
And he is an assistant professor.
All right, thanks for the introduction. My name is Jarrell. Today I'll be talking about our work on characterizing and optimizing parallel garbage connection on multi-core systems. And beyond that, we'll also share with you some of our insights for multi-core scheduling for parallel programs in general. And this is a collaboration with Kunso and Hongjiang from University of Texas and Arlington, and also Witty from University of Nebraska, Lincoln. So the last decade has witnessed the rise of multi-core architectures, including and as well as other forms of hardware parallelism. So to explore the parallelism on hardware, in particular multi-core processors, different layers of the software stack, they devise different mechanisms. So for user space applications and runtime systems, they divide the original sequential problem into parallel tasks and assign them into two different parallel threads, while the operating system schedule parallel threads onto multiple cores. Another important issue of parallel programming is synchronization. There are various designs of synchronization trying to minimize the overhead, especially the coherence misses in a highly contended environment. However, the interplays between the runtime system, the operating system, as well as the synchronization is not well understood. So from the one hand, the runtime system assumes that there is always a one-to-one mapping between the thread and the core. On top of that, they apply their optimizations. But on the other hand, the operating system, they schedule threads, assuming that the number of active threads exposed by the parallel applications actually represent the degree of parallelism that can be exploited from the parallel application. So if both assumptions or either of the assumptions does not hold, then there could be some harmful interactions between the runtime system, the synchronization, the user space application, and the operating system. So in this work, we find out that this semantic gap can cause significant performance loss for parallel garbage connection. So first, we demonstrate that the OS load balancing can have a big impact on the performance of synchronization. We run Linux-based micro benchmarks of synchronization on a 4-socket machine. And note that we have 96 cores, but only have a 48 thread. So the system is underloaded. So we use the CPU affinity to pin individual threads to different cores to guarantee a one-to-one thread-to-core mapping and have perfect load balancing. So from this figure, from the first benchmark, you can see that the original Linux CFS scheduler did a terrible job balancing those threads for the Futex weight benchmark, and it incurred as much as 80% of the aggregation. One may argue that we should always pin threads to CPUs, but it is not always the case. On the last benchmark, which is the Futex lock priority inheritance benchmark, actually statically pin threads to CPUs will incur 40% of overhead. And also in multi-tenant systems, allowing users to pin thread to cores will undermine the efficiency of resource management in a multi-user environment. So there are multiple reasons that OS load balancing may not always be perfect. First, for today's operating system, only runnable or ready thread can be balanced, or they are even visible to the operating system. Second, there are many other reasons that the operating system will choose not to migrate thread because of data locality in the NUMA system, because of cache hardness, as well as energy savings. For example, in the latest tickless Linux kernel, if the kernel becomes idle for a longer period of time, it will stay idle. It doesn't perform periodic load balancing. So if imperfect load balancing exists in the operating system, then there could be some harmful interactions between sophisticated synchronization schemes at the user level and the operating system. And the parallel garbage connection is one of the case. So garbage connection is an important feature that enables automatic memory management in the Java virtual machine. In a parallel garbage connection, when the memory allocation failure in a heap occurs, then the JVM will stop all the application thread and all mutators. And then when the garbage connection finishes, all the application threads will be resumed. And this period during the GC is called a stop the word pause. And this is a common design for throughput-oriented garbage connection. So for parallel garbage connection, the most important phase is the parallel phase, in which multiple GC threads will run multiple GC tasks to concurrently scan the heap to accelerate the garbage connection. So the first stage of the parallel garbage connection, the GC thread will be assigned with root tasks. Each of those tasks will scan part of the heap to accelerate the entire scanning process to free dead objects. After the root tasks are exhausted, if there are still some idle GC thread will run steal task, trying to steal some actual work from the GC thread that are still doing root tasks. And this is the way to balance the load between GC thread. So after a certain amount of steal attempts have been finished, if all the GC tasks have finished the steal task, then they enter a distributed termination protocol. Once all the GC threads they are terminated, then the final task will synchronize them, and then the parallel phase of the GC will end. After the final phase, the entire GC will end. So the parallel GC in the hotspot JVM uses a centralized task queue to assign tasks to GC thread. There is a centralized GC task manager at the beginning of each GC. It will insert GC task into the centralized GC task queue, and from the other hand, the GC thread will fetch task from this queue. And this GC task queue is protected by a monitor. This monitor consists of a condition variable as well as a mutex lock. The condition variable ensures that if the GC task queue is empty, anyone who tries to fetch task from this queue will be put into sleep. And the mutex lock will guarantee that at one time there is only one GC thread can access the GC task queue. So when all the GC tasks are completed, then the GC task will become empty. Then anyone who sleeps on this who fetch task from this GC task queue will put into sleep until the next time the next GC begins. So the key design in this monitor is the native mutex lock in the hotspot. This mutex lock data structure is not only used by the GC, but also used by all the application threads of Java. So this is a very sophisticated design. It has three key designs that are optimized for efficiency and scalability. First, when the lock is not contended, there is a fast path for lock acquisition. This is based on atomic instructions, compare and swap. And there is also a slow path for contended case. So if there are multiple threads competing for the lock, if allowing them to compete the lock simultaneously, then there could be a lot of cache coherence traffic when the lock is released. So the mutex lock in the JVM implement a sophisticated queue structure. So basically, when all the GC threads are sleeping on the condition variable, when the next GC begins, instead of waking up all the GC threads competing for the mutex lock, it will first move all the GC threads without waking up them to the CXQ queue, which is the beginner queue of the mutex lock. Then one thread will be picked up at the lock owner, and when the lock is released by the lock owner will pick up the heir of the next lock owner. So this avoids waking up everyone, will reduce the cache coherence traffic. And there is another important design in the GC, in the mutex lock, is called a competitive handoff. So instead of directly passing the lock to the on-deck thread, which is the next lock holder, the lock owner will make the lock available for everyone. So in case that the on-deck thread is preempted, which is called the lock waiter preemption problem, the lock is still available for other threads. So if there is a new coming thread coming to the system, then they still use the fast path to get the lock. So this will improve the system performance. But in a real system with imperfect load balancing, this could cause problems. So let's assume that when the JVM begins, at the boot time, because the heap is empty, the application is not started yet, so all GC threads will be created by the JVM first. Since all GC threads will be created but there is nothing to be done, they will immediately go to sleep. When you create a thread from a parent thread, all the threads will be default created on a single core. Since all those threads, they run very shortly before they got put into sleep, there is no chance for the operating system to balance them. So all the GC threads will be sleeping on the same core. So after one lock holder is woken up, and lock holder pick up the on-deck thread, both threads will be on the same core. And since Linux does not do a good job of load balancing, and also the parallel GC implements a dynamic work assignment, which means if a thread is fast, they can fetch much more work than other threads. So the lock holder is currently running on the CPU and may not be preempted by the on-deck thread, and the lock holder can continue runs and continuously fetch tasks from GC task queue. So there could be a serialization at this point. Since all other lock contenders are still in the sleeping queue, are not visible to the operating system scheduler, so there's no way for the operating system to balance them. So we observe a significant loading balance among a GC thread. So most of the work is done by only two threads. One is the lock owner, and another one is the on-deck thread. And also it is expected that we see a significant loading balance on the cores. So most of the GC threads are stacked on two cores. And also there is a side effect can cause inefficient work stealing. Since most threads have nothing to be stolen, the original work stealing algorithm doesn't work effectively. So from this figure, we can see that even the entire GC time is dominated by the stealing task, and as well as the termination protocol of the parallel phase. So how does work stealing work? It's very simple. So it's randomly pick up two GC threads and try to steal from the thread with a longer queue. And each GC thread will try 2n times. If all attempt fails, then they will enter a terminated state. If all GC threads are terminated, then the parallel phase ends. So if the two random choice stealing is not effective, if most of the threads have nothing to be stolen. So we devised two optimizations to address those issues. First, we dynamically bind the GC thread to separate cores. We try to bind the GC thread to cores that with the least node. But if the system only has one JVM or one Java program, we don't need this dynamic binding. We simply static bind to different cores. This seems to be a very naive solution, but this is the solution that we came up with many other approaches that all failed. And also we propose a optimized work stealing algorithm. So instead of randomly pick up 2 threads to steal, we propose a semi-random stealing. We pick up 1 random thread, then we pick out a thread from where we successfully fetched work. And then also we reduce the number of attempts before we enter terminated state from 2 times n to 2 times n live. N live is the number of GC threads that are currently having work to be stolen. So we did some experiments. The overall conclusion of our experiment is that different applications, they may suffer differently from the issue, but we observed some applications that had very serious performance degradation. So our approaches had consistent performance improvement across all the applications. So some applications suffer more, some applications suffer less, but no applications suffered from our approach. So from this figure, we can see that with the very simple GC thread pinning approach, the work among GC threads are much better balanced. And each thread will be able to fetch the real GC tasks. And also, we had some performance evaluation with the decouple benchmark and also the spec JVM benchmark. For all the benchmarks we select, those are the benchmarks that are sensitive to parallel GC, which means if we increase the number of GC threads, the performance will increase. And also we set the heap to the 3 times of the minimum heap of each benchmark to guarantee a reasonable setting of the heap size. And also we guarantee that for all the systems that we tested, the number of cores are larger than the number of threads. So all the systems are underloaded. There is no contention at all. So, and also we test the different approaches. The thread affinity optimized stealing separately to isolate their effect, and also we evaluate the combined effect. So overall, thread affinity plays a bigger role in the performance improvement. But on top of that, optimized scaling can also improve about 5% of the performance. And also different applications, they benefit differently from our approach. For decouple benchmarks, they benefit more, but for spec JVM, they benefit less. And also, if we look at the GC time, the reduction of the GC time, because the overall improvement depending on how much percent the GC was in the original execution time. So note that our optimization only applies to GC. We didn't touch any application thread and all the application code. So the improvement on the GC time were more significant. And also we test the application results with Spark running in-memory Java-based computation. And we can achieve up to 13% of improvement. And also we test with Cassandra database queries, latency-based, and we can improve the tail latency. And also there were more results on the paper. We test the scalability, different heap sizes, multiple Java programs, and also we compare with one of the existing work, also utilized GC affinity to improve the data placements of JVM, although we think it's quite different from our work. So in this work, we find out some problems with the parallel GC to interact with the operating system if the operating system doesn't do a good load balancing work. So we observed that the frequency of load balancing increasing the frequency of load balancing can mitigate the problem. So for example, if you disable and enable the simultaneously multi-threading, this will increase the frequency of load balancing, so it will help mitigate the problem, but doesn't entirely solve the problem. So our approach can still improve on top of that, and also disabling power saving, ignoring the NUMA locality can also help the problem. But we believe that this is a much bigger problem than just the parallel GC, because there is an inherent trade-off between synchronization and multi-core load balancing. So first, from the perspective of the synchronization, most optimizations want to limit the concurrent lock contenders to minimize the hardware overhead. But from the perspective of the operating system is most effective if all threads are active. And beyond GC, we observed up to 68% of performance difference if we pin threads to separate cores compared to baseline Linux scheduler in the PASAC benchmarks. So there are 2 implications in the future work. First, there should be a more general solution in the OS scheduling, because we argue that thread pinning is ugly solution, but we still haven't find a good solution for that. And also, we should think about the synchronization optimization. We should consider the operating system's effect. Take into effect. For example, a naive conclusion for synchronization optimization could be, let's replace blocking-based synchronization with a spin lock, because spin lock will keep all the threads active. They will be more friendly to the operating system scheduler. We don't have a conclusion slides because we don't have a very good solution. And also, I'm happy to take questions. Thank you.
Thank you. We have time for one quick question. Can you set up?
Christopher Stewart, Ohio State. So you've sort of assumed a lot about the cores and the underlying hardware, which is sort of anti-design principle of a Java virtual machine, right? I'm wondering very concretely how you dealt with hyperthreads, right? Which may have a different behavior if you were to pin hyperthreads as if they were cores. Mm-hmm. And more generally about your thoughts on just sort of breaking that division between virtual machine and OS by assuming that a core is a physical processor.
So in our paper, we had both the results of hyper-threading enabled and disabled. So we had a very similar observations. And back to your question, yes. So for virtual machines or Java virtual machines, in order to decouple from the underlying hardware, we always have assumptions. But the problem is that in most cases, those assumptions may not hold, and that can cause some subtle, sometimes very significant problems. So that's why sometimes we need to break the barrier a little bit, try to bridge them, and then make them coordinate or work better together. Thank you. Where's my lab? Oh, thank you.
Okay. Let's moving on to the next paper about a data-centric operating system architecture for heterogeneous computing. This is a collaboration between multiple entities, as you can see on the slides, and the talk is given by Shang Wu.
Thank you for the introduction. Today I'm going to talk about data-centric operating system architecture for heterogeneous computing, named Solars. This is a joint work with my fascinating collaborators, Unhak, Mohan, Sanidhya, Stefan, Hisung, and Professor Tasuki. These days, literally, we see our announcement of new process architecture, we call that Cambrian explosion of process architecture. For example, we actually see the conflicting trends. For example, we see a specialization of the general purpose processors like Xeon Phi. At the same time, GPGP also try to extend their coverage of the workload to make it more general. Excuse me. And also, we also see the specialization of the coprocessor optimized for the killer workloads such as deep machine learning. At the same time, we also see the I/O performance of the I/O devices becomes blazingly fast. So now the storage device performance is blazingly fast, and network performance is blazingly fast. Our research question is how to fully exploit such a fascinating hardware devices without pains. So we believe that we have to achieve the widely good performance. At the same time, we want to maintain the ease of programming. In the rest of the talk, I will give you a brief background how the existing approach, how to deal with such a fully exploit the coprocessors and the fast I/O devices, and then present our approach named Solos, and then finally present our evaluation result. In order to fully exploit coprocessors and fast I/O devices, the most popularly used approach is host-centric approach. So, and OpenCL and CUDA, which is the pretty widely used techniques, frameworks, actually follows the host-centric approach. Suppose that our coprocessor application wants to fetch the data from the I/O devices, for example, the SSD, and then host application first have to load the data from the SSD to the host memory, and then copy the data to the coprocessor memory. As you can see here, the obvious problem is that we have to copy exactly the same data twice. So the redundant data communication is one of the main problem of the host-centric approach. And actually, it raised the PCIe bandwidth and also increased the communication latency. And in order to hide such the overhead, the coprocessor application have to typically interleave the communication and computation, and that makes the program too complex and hard to optimize. The other more radical approach is the coprocessor-centric approach. The key idea is to run the I/O stack on top of the coprocessor. So conceptually, the coprocessor operating system, applications directly control the I/O devices or virtual I/O devices and then fetch the data from the I/O devices. It's very good conceptually, but in reality it's pretty difficult to achieve because in many cases it requires significant effort to porting the I/O stack to the coprocessor, and also it completely missed the opportunity to fully exploit the fast and powerful host processor. To address these problems, we present the Solus, which basically takes the split kernel approach. In the Solus project, what we want to achieve is these three. The first one is we want to make the coprocessor programming easy. At the same time, we want to best use of the different coprocessor architecture. For example, the property of the host processor and coprocessor are quite different. Host processor has less number of CPU cores, but each CPU core is pretty fast. And coprocessor has massively parallel, but its core is relatively slow. At the same time, we want to achieve the system-wide optimizations. Actually, achieving these three goals at the same time is pretty challenging. For example, in order to maintain the ease of the programming, we want to provide the I/O abstraction in the coprocessor, but running the I/O abstraction, I/O stack on top of the coprocessor is not a good idea because I/O stack is branch divergent and sometimes very difficult to parallelize. And also for the system-wide optimizations, we need a system-wide global information. In Solus architecture, we take the split kernel architecture, which is composed of data plane operating system running on a coprocessor and control plane operating system running on a host processor. Data plane operating system, which runs on a coprocessor, provide the I/O abstraction for coprocessor application, but does not run actual I/O stack. Instead, it delegates actual I/O operations to the control plane operating system. In the control plane operating system, which runs on a host processor, actually runs actual I/O stack for data plane operating system, and also have the system-wide performance optimizations and coordinations. Let's go back to our initial example, reading data from the SSD for the coprocessor applications. In Solus architecture, coprocessor applications simply call the POSIX API, such as file system, open, read, and write, and close. And that system code actually translated into RPC in the data plane operating system, and they send the RPC command to the control plane operating system running on host processor. And the control plane operating system actually runs the file system and controls the device. And let's suppose that the control plane operating system decides to directly copy the data from the SSD to the coprocessor. Then we actually perform the zero copy between the I/O device and coprocessor. Actually, this model has a lot of the advantages. For example, the coprocessor has an I/O abstraction with minimal effort. And we believe that this is the best use of each fat and lean processors. Actually, in this architecture, the I/O operations first have to go through the control plane operating system. Control plane operating system have a global knowledge of entire system. So it is very easy to make a global decisions. So in Solus, we developed 3 operating system services, including transport service, file system service, and network service. And in this talk, I will first present two of our services. The transport service is a uniform data transport layer between the storage I/O devices and coprocessors and host processor. This should provide a high performance. And this actually providing the high performance among the devices are pretty challenging. One of the challenges is that we have to provide a kind of uniform data transfer among the devices. And also, we have to somehow deal with the high contention in massively parallel coprocessor. And the other important thing that we have to take care of is that the performance, asymmetric performance between host processor and coprocessor. In order to deal with these three challenges, we took these approaches. For the uniform data transfer, we mapped the physical memory of each the I/O devices and coprocessor to the PCIe window in the system, so the host can uniformly address any of the physical memory in I/O device and coprocessors. To tame the high contention, we proposed several techniques, such as the combining. That is basically the batching technique, and replicating the control data for the data plane transport service to minimize the PCIe transaction. And also, we interleave the control operation of the transport service and actual data transfer to maximize the actual data transfer. And also, our transport service is the flexibly configurable to exploit the asymmetric performance. For example, if the user of the transport service wants to use the fast host DMA engine instead of a little bit slower coprocessor DMA engine, our transport service can be configured in that way. So please see the details and interesting optimization in the paper. On top of the transport service, we implement the file system service, and actually it has two operation modes. One is the peer-to-peer operation, and the other one is buffered mode. In the peer-to-peer operation mode, the coprocessor application just runs the POSIX file system interface, and then that is actually translated into the RPC code and delivered to the control plane operating system. And control plane operating system actually controls the file system and devices. And in this example, let's suppose that we are copying our data from the SSD to the coprocessor memory. Then in the peer-to-peer operation mode, host processor setup controls in this case, NVMe SSD, target address of the NVMe SSD to the physical memory of coprocessor. So the actual data is directly copied from the SSD to the physical memory of the coprocessor using the DMA engine of the SSD. This is a true zero copy of the data between coprocessor memory and SSD. So we can minimize the data transfer without redundant data copy. This peer-to-peer operation looks very nice, but this is not a silver bullet. For example, in the current generation of Intel architecture, if the coprocessor is attached to the socket 1 and the NVMe is attached to the socket 2, PCI packet have to cross the QPIe boundary, and that actually takes a lot of time and much slower. So in those cases, the host side buffering is better. And also another scenario that the buffered operation is better is that if multiple coprocessors have to access the same data on the one SSD, then the host side buffer cache is better. So we implement Solus using the Xeon-Phi coprocessor, PCIe type Xeon-Phi coprocessor. And actually Xeon-Phi runs the embedded Linux. So we actually modify the embedded Linux on Xeon-Phi and the Linux kernel in host to implement the Solus. And for the evaluation, we used 4 Xeon-Phi and 4 NVMe SSD and 100 gigabit Ethernet. Our question in the evaluation, we want to answer the two questions. The first one is how our Solus operating system service is performant. And the other one is that improve the Solus services in terms of performance, how much that affect the real performance of the real-world applications. And this graph shows the performance of the Solus services. In the left-hand side, we ran the file random read operations on Solus. And in the right-hand side, we ran the socket 64-byte ping-pong applications for the TCP. And the client is on the other machine. And in the green line actually shows the performance of the applications running on Xeon-Phi with Solus, and the blue line is the performance with the stock Linux kernel running on Xeon-Phi. As you can see here, the the Solos I/O performance is 19 times faster than the stock Linux kernel on Xeon Phi. And if the request size is large enough, in this case 12 kilobyte, we can achieve the maximum SSD bandwidth. And for the TCP latency, 99 percentile TCP latency, the Solos' latency is the 70 times shorter than the stock Linux kernel on Xeon Phi. In order to understand why Solos, what is the main contributor of such a good performance in Solos, we did a performance breakdown. And as you can see here, one of the biggest contributor here is that we got the significant performance gain in the data transport, since our data transport layer considers asymmetric performance and tames the massively parallelism and so on. So we wins a lot of the performance gain here. And the other one interesting thing is that since our data plane operating system layer running on Xeon Phi is so thin, so the time spent on running the I/O software stack is much shorter. In the paper, we ran two real-world applications, text search and image search, and in this talk, I just present the image search applications. In the setting of the image search applications, we used 4 Xeon Phi and 4 NVMe SSD. And in the Xeon Phi, we ran image search engine, and the image search database is on NVMe SSD. That is a shared read-only data. And the image search query, actually, there is a small JPEG file actually delivered through the network. As you can see here, Solos, the image search engine running on Solos actually performs 2 times faster than stock Linux on Xeon Phi. To conclude the talk, we present the Solos, which is a new operating system architecture for coprocessor and fast I/O devices. Solos basically takes the split kernel architecture composed of control plane and data plane operating system. And we will soon release the source code, so please stay tuned. And this is all I have, and I'm happy to take your questions.
Okay, yes.
So can you explain how this is different from GPUFS and GPUNet?
Yes, actually, we actually also inspired by the GPUFS and GPUNet. Actually, GPUFS and GPUNet try to port in file system and network services, especially the RDMA services, to the GPU, and they try to handle a lot of the GPU-specific optimization. But we try to find a kind of general design principles to how to deal with the fast I/O devices and coprocessors. Thank you.
So you had the one case where you did buffering in the control plane OS. Is that in any way notably different than the older approach you were talking about replacing, in which normally the application would copy into system memory and then copy to accelerator memory?
Oh, actually, in case of the buffered mode, basically that is conceptually it is the same with the host-centric approach, in the sense that the data have to be copied twice. But the important part here is that everything handled under inside the Solos kernel, and if the multiple coprocessors try to access the same data, that will be automatically handled by the Solos kernel. That is the difference.
Okay. There's one more.
Hi, Chagai from the Technion. So with the new advances in coherent shared memory for accelerators and things like unified virtual memory from NVIDIA, what would be the role of Solos in such systems? What would be the role of Solos operating system in these kind of systems?
Could you repeat the previous part of your question?
I'm asking about new systems with coherent shared memory between accelerators and host memory.
Yes, actually, this is very interesting and good question because recently many people actually propose a coherence between the coprocessor with the host processors, but actually still we need to somehow address how the coprocessor application have to access the other I/O devices. So in that sense, that we can definitely can leverage the coherence to simplify, for example, the Solos design, but I think that we still need how to deal with the I/O, provide the I/O abstraction and the I/O services in the coprocessor.
Okay, then let's thank the speaker again. Okay, next speaker. Is that you? Okay, while the next speaker is setting up, the next paper is a collaboration between Purdue University and Peking University. It's Power Sandbox, and the talk is given by Li Bai. The floor is yours.
Second year, actually. Thanks for the introduction. Good morning. Today I'm going to talk about a fresh new perspective on rethinking power awareness. This is a joint work between me and Tin Du-Xu, who contribute equally to this work, and Mengwei Xu Xuanzhi from Peking University, and of course my advisor Felix Lim. Let's get to it. As previous speakers have talked about, that I/O performance or your multi-threading performance matters more and more in modern systems. Also, the trade-off between energy efficiency and the performance matters more and more to applications. As a result, these applications demand to know their power so that they can adapt accordingly, becoming power awareness. A power awareness is a line of research work starting in 1999 and up until today. For example, these applications will vary content fidelity, or they will reduce their I/O activities based on their power requirement. Or in the area of approximate computing, they may adjust the algorithm frequency. So what power knowledge matters to an application? If you look at this figure, an application not only its binary, but also its vertical environment, which in this case is the software and hardware stack, impacts the system power. As a result, the system power changes and it is prompted to the application so that it can adapt accordingly. There is a classic two-step approach to acquiring such power knowledge. First, metering. Metering is collecting the system power either through software modeling or direct measurement, as exemplified by multiply work. For example, you can use syscall to map these system activities to the whole system, or you can collect the kernel activities and come up with a software model, or you can just directly measure the battery power through voltage and current, of course. And the second approach is accounting, where accounting is attributing the collected system power to these individual applications that cares about its own power, and it's got many, many accounting heuristics. For example, splitting them according to the syscall use or CPU usage, and you may just evenly split them. However, there is something wrong. For metering, we believe it is fine. You can use either software modeling or direct measurement, as we have said. Just measure the current, that's fine. However, we believe that for the accounting, there is a flaw because there is simply no correct heuristics. And it's due to one problem, a problem we dub as power entanglement. What is power entanglement? If you look at the dictionary definition of entangle, it says objects to become correlated, and they remain correlated even though they are separated spatially. Then we try to come up with the old definition of power entanglement. Here it is. A work-conserving operating system, which usually multiplex or aggressively multiplex applications on hardware. It also allows concurrent applications to impact the system simultaneously. As a result, these impacts become inseparable. What is nice about this definition is that it does not only reflect the original definition of entangle, but also it reveals the fact that power entanglement is rooted in commodity operating system. We identify 3 causes of power entanglement. First, concurrent use of hardware. As a common practice, multi-core CPUs run tasks concurrently, and these tasks co-running on this CPU share resources, for example, last level cache. As a result, such sharing leads to power entanglement. If you look at the figure below, process A running alone on this quad-core CPU, and process B running alone on this quad-core CPU. If you look at their power, the sum of their power is not equal to them running together on this quad-core CPU. The second cause is called blurry request boundary. It applies to most accelerators, because also, as a common practice, these devices usually buffer the commands and requests from user application and process them in batch, and of course, asynchronously. As a result, these in-flight requests overlap in time, and thus the power impacts become inseparable. The third cause is called lingering power state. As modern devices become more complex, they usually have non-trivial power states, which contribute differently to the total system power. And most notably, it's tail power. For example, if you tell your Wi-Fi NIC to shut it down, well, for most cases, it will actually not. It will stay active for quite a while, and this contributes to the system power. The very first problem that power entanglement brings is a reasoning difficulty. Assuming you have 2 network transmissions, which transmits 2 packets of the exact same length. However, according to the prior accounting approach, the second transmission will likely to have more power because the tail power is attributed to the second transmission. When such information is prompted to the application, it is often have no idea what is going on because it is doing exactly the same thing. This creates reasoning difficulty, and the application does not know how to reason about the correct behavior. The second problem power entanglement brings is power side channel. As has been demonstrated by much prior work, it is a powerful side channel that can leak security-sensitive information, such as your encryption behavior, authentication procedure, or GUI state. We conducted a simple experiment where we run 2 applications using the same GPU, and the attacker is trying to infer what the browser is visiting. By only observing the power trace of the total system power, the attacker is able to increase the success rate of such attack by 6x, which is actually much higher. What is worse, fine-grained power metering further exacerbates this. So let's take a quick pause and look at what are the takeaway messages as of now. First, we argue that prior work is fundamentally flawed because, accounting heuristics. They're trying to separate something that is inherently inseparable because of power entanglement. Second, when we are talking about power, we have to be very careful, since disclosing more than enough power information is not only useless, but also harmful. To respond with such a problem, our solution is Power Sandbox, short for PSBox. It insulates the power impacts from all other co-running applications within the same system from the lowest level, which is kernel, and allows the application to observe the power of its own vertical slice of the software-hardware stack. We implemented PSBox behind 3 key ideas. First, kernel enforces PSBox boundaries, where we introduced 2 types of resource balloons to ensure this. A, spatial balloon. It is used to confine spatial concurrency of OS schedulable resources, for example, tasks. A specific example would be a spatial balloon at one time can only be either an application from the same PSBox or an idle task. So that at one time, only the PSBox application or an idle task can occupy the CPU. B, temporal balloon. It is used for most accelerators because we have mentioned the in-flight requests will cause the power to entangle and become inseparable. We introduced temporal balloon so that over a period of time, only the requests from PSBox can be served. The second idea will be building the applications in PSBox. As we have introduced the 2 types of resource balloon, introduce the loss sharing opportunities To ensure the fairness among all other applications co-running in the same system, we have to charge such load sharing opportunity to PS-Box applications. For example, the PS-Box application will be scheduled less frequently and executed in lesser time in future. The third idea will be virtualize the power state, because this is the only way when a PS-Box application leave and re-enter, it can perceive the consistent view of hardware power states. So, how does the spatial balloon work in action? This graph shows a simple experiment that we've done, where x-axis stands for time, y-axis stands for power, and these cute little bars with different colors stands for CPU scheduling timeline. We run two applications in this dual-core system, which is Calibre 3D and Body Track. And as we can see, the original design, this power of the two applications actually interleave freely. However, when we decide to put Calibre 3D into PS-Box and observe its power behavior, when the PS-Box application is about to schedule in, as we have said, because of the spatial balloon, we have to send the inter-processor interrupt to the other core to shoot other tasks down to ensure that only a PS-Box application is running on the system. And because in this benchmark, Calibre 3D happens to be a single-thread application, so the other core has to be an idle. Then the PS-Box application is running freely and updating its scheduling stats, which here we call scheduling low. When the PS-Box application is scheduled out, we do this scheduling redistribution, and it repays the lost sharing opportunities. For example, it is actually executed in lesser time in future. How does temporal balloons work in action? Similarly, we run this experiment on DSP, a common accelerators, where 3 applications are run. And as we can see, the requests coming from these applications overlap, as well as the power. First, upon entering a temporal balloon, we have to ensure that no in-flight requests exist that affect the total system power, so the phase 1 will be draining other requests. And because there are maybe requests from PS-Box are buffering at this draining phase, during phase 2, which is upon entering PS-Box, we have to flash those requests immediately. Then the system go ahead and serve these requests. After it leaves, because it also has to ensure that all the PS-Box requests are properly served. So this white gap shows that we have to wait for the kernel is notified for the compilation. Then the system go ahead and flash other requests buffering at this time. We implemented PS-Box on 4 subsystems, or in the kernel level, namely CPU, GPU, DSP, and Wi-Fi NIC, atop of Linux kernel version 4.4. And in terms of metering, we actually prefer high resolution and high frequency power sample. That's why we assemble this prototype, hardware prototypes, which is quite cute. In evaluating PS-Box, we have a set of questions in mind. Does PS-Box achieve its goal? Does it eliminate its power entanglement? Of course, otherwise why would I be here? In this experiment, we run dgen application alone on DSP as a reference. X stands for time, and Y-axis stands for power. The number stands for the accumulated energy. To compare with the existing approach, which is using different accounting heuristics, we run dgen co-running with the other application called sgen. By using existing approach, as we can see from the graph, it is visually largely different from what is running alone. And the accumulated energy varies by 50%. It gets worse when we co-run it with 2 other applications because of power entanglement. Then, after applying PS-Box, we are able to preserve a visually similar power graph and as well as accumulated energy. We are able to reproduce these experiments on all 4 subsystems, and more details can be checked out in the paper, which has no math and easy to read. Also, PS-Box, of course, has overhead. First, it causes the latency to increase because PS box switches. As we have said, the temporal bloom and spatial bloom will incur, say, scheduling events. For example, you have to send the IPI to other core, and such interrupt handling will take about tens of microseconds. And for the command drain in temporal bloom, it will take about 10 milliseconds. Wi-Fi NIC is kind of an interesting case because first, the hardware is wimpy, and second, it's got firmware internal batching, which can increase the latency by tens of milliseconds. Throughput loss is due to loss sharing opportunities. In a low resource contention scenario, the total system throughput loss is contained within 10% in the CPU's case, and for GPU and DSP, we're able to contain it within 5%. And also, it is worth mentioning that even in a heavy resource contention scenario, because we build those loss sharing opportunities to PS box application only, these throughput loss is confined to the application that uses such service. And other applications within the same system remain largely unaffected. We're able to build power-aware applications because of PS box, where we build a virtual reality application in 2,000 lines of code. And in this application, a user waves his hand, and its gestures is recognized by the camera and thus rendering a wave. In this application, two tasks exist. First, gesture recognizing. Second, rendering task. Without PS box, a rendering task cannot simply differentiate itself with the total system power because of power entanglement. However, after applying PS box, it can know what power it uses and thus can adjust its behavior accordingly, as we can see from the graph. The rendering tasks become less frequent, and it means that rendering fidelity is lowered for low power. In conclusion, there are three key contributions we made in this work. First, we argue that traditional approaches stands on the flawed ground because they're trying to separate something that is inherently separable. Second, to respond, we advocate a novel OS principle called Power Sandbox to eliminate power entanglement as well as power side channels. Further, we demonstrate that PS box is actually practical and it facilitates construction of power-aware applications. PS box is open source at the following link. Thank you for your attention. That concludes my talk.
Questions?
Hi, this is interesting, but I'm confused. I'm not sure whether you actually, well, it seems that you, by separating out power usage in order to increase accounting of power, which is not really what matters is energy, you get much reduced resource utilization and therefore overall increased energy use. So what have you gained?
So, because PS box is intended actually as a pay-as-you-go service, which means that it's a service and you call the price to know your system power, but it's not a specific, say, energy optimizing strategy for you to improve the total energy efficiency. So it's just a way that the application can observe a consistent power knowledge, and it's just a service. And after you're done with the service, the system just runs freely as usual, and it's unaffected.
This is good work. It's a very systems approach to a problem that I've seen other people look at. The other approach that I've seen taken, Chalet Ren's group at UCR, I've looked at Shapley's metric, where you sort of run every possible combination of workloads and you extract an average impact on the system. So it's a little bit more of a workload profiling offline, and then you, so can you compare the two or what you think about?
First, PS box is actually a runtime system, so it actually separates these power impacts from the lowest level in kernel and at runtime. So this is the first difference. And the second, and I'm not sure about the offline profiling, because if you're running these applications offline, even if you're profiling offline, you're still not, say, separating these power impacts from different applications within the same system. And it's even if you're collecting those system power and you're trying to we argue that even if you start attributing this power to individual applications, you are probably starting at the wrong place. Thank you.
How easy is it to turn on and off the PS box? Is it possible for me my application to turn it on for half a second, get a few samples, turn it off for 3 minutes, and then...
That is right. So PSBox is intended to be we expose PSBox API through procfs in our experiment, and it can be, of course, implemented as a syscall. And also, it is actually intended for applications developers that cares about one phase of execution. So whenever you enter a critical phase that you cares about its own power, then you turn it on. Then after you finish executing, then you turn it off. So it's it's very likely that you can use it for, say, past 0.5 second or 0.5 second, even or longer time. And you will have different methods to say how you can gather those power traces. You can say polling, or you can tell the system to buffer it, and then you acquire it later.
So, Boris Greit, University of Edinburgh, really interesting work. I'm trying to understand why this is useful in practice. So, I understand that if you temporally and spatially isolate an application, you can get a really accurate power measurement, right? That makes sense. But what does that mean? If the real deployment, if I just want to do a sample, but the real deployment, things are spatially and temporally are actually co-located, that sample is not very representative, right? And if I always do this isolation, that seems really wasteful, right? So why?
So I guess your question would be, why do you want to separate or use this service? Is that what you're asking?
Yeah, right. You're essentially inflicting a pretty heavy, what appears to me, performance penalty, right?
Yeah.
By doing this type of isolation. So why is this useful in practice? Just to do a measurement.
Yeah, because as a as we have said, the power entanglement actually creates reason difficulty. If you're looking at the application that's actually care about its own power, which actually is a research work. It's pretty long, and they actually have a very fine-grained requirement for such critical phases, observing these critical phases. And other coarse-grained or other accounting heuristics, first, of course, they have overhead. Even if you sample those cycle counters, if you cycle it high frequent enough, it will have a very large overhead from our experiment. And then second, it's very fine-grained, and you can turn it on when you are caring about, say, this one network transmission, or you can just turn it off when it goes away. Then that's how it becomes practical.
Okay, thank you. We are out of time. Let's thank the speaker again. Okay, next speaker presents model-driven computational sprinting. This is collaboration between Ohio State University, IBM Research, ABB Corporate Research, and Denison University. And we can almost start. Floor's yours.
Thank you. So computational sprinting improves application responsiveness by pushing the CPU beyond its thermal limitations. This can be done using different types of sprinting mechanisms, such as DVFS, as well as core scaling. To the left, we have an illustration of DVFS, where on the x-axis there's time, and on the y there's clock rate. We see that we can sustain 1.3 gigahertz, and during a sprint, we will increase the clock rate to 2.2 gigahertz for a short period of time, and then revert back to our sustainable frequency. Likewise, with core scaling, we can do the same, where we start off with only 2 cores, and during a sprint, we will increase the number of cores from 2 to 4, and eventually revert back to our sustainable number of cores. Of course, the duration of a sprint is dependent on the sprinting budget. And for example, we can say that the total time that you can sprint on AWS burstable instance is for 6 minutes per hour. Now, fundamentally, these budgets can be defined with scarce resources in your system, such as the thermal capacitance, as well as energy and CPU cycles if you're dealing with co-located environments. If we add in a trigger with the mechanisms, the sprinting mechanism and budget, we now have a sprinting policy. A trigger simply is a threshold that determines when we want to sprint. Many SLO-driven services use timeouts to trigger sprinting. So here's a sprinting example showing how SLO and a sprinting policy can work together. So let's say that the SLO specifies that we need to complete 99% of our queries in 2 seconds. And our sprinting policy says that we can sustain 1.3 gigahertz and we want our timeout to be 1.5 seconds. And during a sprint, we would like to increase the frequency to 2.2 gigahertz until, one, the query completes, or our 50 joule budget is exhausted. So there's 2 root causes why a sprint will be invoked. The first is if the execution is longer than normal, and so we're going to sprint only the tail end of our query. The second one is if we have a longer queuing delay. So we're going to end up sprinting a larger portion of our execution and consequently use more energy in our budget. Now, while we're sprinting, there's dynamic runtime factors that can impact response time. These can be queue length, speed up from sprinting, as well as the remaining budget. So exactly how does the state-of-the-art and in practice do they set the timeout policies, our sprinting policies, and the budgets? Well, in practice, they use the exact same sprinting policy for all workload types, like in the AWS burstable instance example. And for state-of-the-art, they have 2 popular approaches so far. They target slower than expected queries, and they target high utilization. Of course, these approaches by nature are heuristic and can perform poorly if system conditions change, as well as be very sensitive to parameter settings. Our solution is model-driven computational sprinting. This allows us to predict the expected response time as well as explore many sprinting policies so we can find high-performance settings. This approach has 2 major components. Number 1, we use first principles to model and capture the sprinting fundamentals, as well as machine learning to characterize the effects of runtime factors on response time. So now I'll talk about first principles for sprinting, followed by effective sprint rate, and then model evaluation. So the way that we deal with modeling the first principles of sprinting is that we design a discrete event queuing simulator. Traditionally, queuing only has 2 inputs into the simulator, first the arrival rate and then the service rate. But if we want a sprinting capable simulator, we have to add additional parameters. That is the sprinting policy, which is the sprint rate, timeout, and budget. Here, what's principle about this is that we can compute the response time for each job given the queuing delay, the processing time, and the timeout. And of course, then we're able to predict this response time. So exactly how do we get these inputs? Well, we use offline workload profiling, where we vary the workload conditions as well as the sprinting policies. From there, we can measure the service rate and this marginal sprint rate via profiling. Now, exactly what we care about is the marginal sprint rate. This is just the processing time when the entire query execution is sprinted offline. Next, we'll look into effective sprint rate, followed by model evaluation. So, offline profiling only helps describe sprinting in isolation. This is the system properties that we typically experience in a live workload that can really impact response time are not considered. So exactly why is the offline profiling very inaccurate? Well, we found 2 paradoxes in these cases. The concurrency paradox is this: a sprint that alters just 1 query execution can affect the response time for many queries in the queue. Also, with the phase paradox, we have this case where if 1 query execution is sprinted, it will consistently yield less speed up under a live workload versus the offline profiling. So one solution to deal with this is to use machine learning to learn response time. Of course, response time is going to be very complex and nonlinear in nature, and it's going to require lots of training. Well, what we found out through our observations is instead we can use our simulator, which is first principles of queuing theory, and just allow the machine learning component to learn this effective sprint rate. So now this reduces the burden on the machine learning and as well as the amount of training data. Exactly which machine learning approach? We use the random decision forest, which combines multiple deep decision trees. For details on this, it's in the paper, but the two main reasons is that it reduces the bias due to runtime factors as well as reduced prediction variance. Now we'll look into our model evaluation as well as a case study for a real-world application. So the way that we evaluate our model-driven approach is by setting up 7 services, 2 Spark workloads as well as 5 NAS workloads. We vary the sprinting policies as well as the workload conditions. We look at different sprinting mechanisms as well, like DVFS and core scaling. And in particular, what we do is we change the arrival rate as well as the sprinting policy and predict the response time with our solution and compare that to our observed response time. So there's 3 goals that we get out of our evaluation. First, we want to compare exactly how well does our approach generalize across workloads and sprinting mechanisms. Secondly, we want to see if we implement a different solution, how well does it compare to our model-driven approach? And can we use our model-driven approach to discover better sprinting policies for a real-world application? So this is our first result showing the median error across sprinting mechanisms and workload types. We selected workloads such that some are memory bounded, while others can benefit from a lot of parallelism, and of course others that only benefit from sequential improvements. We show that our approach can be between 93 to 97% accurate, regardless of the sprinting mechanism and workloads that we tested. Here we show how our approach compares to an artificial neural network. We designed the neural network such that it's a fair comparison between our random decision forest and it. So in our random decision forest, we have 5 trees. In the neural network, we have 5 fully connected layers. And we do some more tuning, such as input normalization, to really increase the accuracy of the neural network. And we showed that our approach still requires 6x to 54x less data to have comparable accuracy with the artificial neural network. So here we look at AWS burstable instances. This falls in the computational sprinting paradigm for 2 reasons. One, the workload is limited to 20% of the CPU. And while the CPU credits are building up, which is the budget, if for some reason that workload or service demands more than 20%, it then sprints to 100% utilization of that CPU core. This can only be done for a total of 6 minutes per hour. We test 2 major implementations. One where we have big burst, where this is going from 20% to 100% utilization of a core, and small bursts where our sustainable is 20% and then we burst up to 60% of the CPU. So here we show how our model-driven approach can scan through multiple sprinting policies and find good sprinting policies that minimize response time. We, of course, look at 2 different versions, small and big bursts. We see that the red line is small bursts and how there's a major difference between just the the small and big bursts. So for the sprinting policy that yields the lowest response time for small bursts is approximately 49 seconds, while for big bursts it's approximately 90-second timeout. So it's clear that there's a profound effect based on just changing our sprint rate when it comes to computational sprinting. And we showed that just through this sprinting policy exploration, we can find policy that will improve response time by 1.4x. Next, we compare our solution to the state-of-the-art. We have Adrenaline and Few2Many. With Adrenaline, their sprinting policy is pretty straightforward. It's a nice heuristic. It sets the timeout based on the 85th percentile of response time. While with Few2Many, they try to find the largest timeout that can effectively use the budget and exhaust it completely. In this table, we normalize the results to our approach. This is based on response time. And we see that for big bursts, we can do about 26% better than Adrenaline and only 6% on Few2Many, but for small bursts, we do significantly better in terms of reducing response time by selecting better sprinting policies. So in conclusion, we show that computational sprinting can reduce SLO violations, but these sprinting policies can have complex effects on the response time and runtime execution. Our solution combines machine learning as well as first principle modeling to predict response time quickly and accurately. We use our modeling approach introduces effective sprint rate that allows us to characterize the speed up from sprinting due to dynamic runtime conditions, and we show that our model-driven approach can be very accurate and also find better sprinting policies that can beat the state-of-the-art by 45%. Thank you. Any questions?
Any question? Anybody wants to go to coffee?
Hi, so thank you for the presentation. So you use deep decision trees for this decision. They are known to be prone to overfitting when they are too deep. How did you check for this?
What's the question about overfitting?
Yeah, how did you check that your model does not overfit the training set?
So this is the very reason why we selected random decision force, because the way that they have multiple trees within the random decision force, they all have to agree on a particular prediction, and so this prevents the overfitting. So this is the reason why we selected that machine learning. If we only use decision tree, you'll have significant overfitting, and then it won't generalize very well.
Okay. Yeah. Does that mean that there was no training versus test phase in the random forest?
Does that mean there's...
Did you use all the data for the...
No, oh, so yeah, we only use 70% of the data that we profile from. Yeah, so even there, we still have very good accuracy results from that.
Okay. More questions? No? Then let's thank the speaker again. Okay, just a quick announcement. The speakers of the next session, please come forward and speak to Peter, who's sitting here, and then enjoy your coffee break.